the 8:55 stop has surprised a lot of people. Me too, actually. So I've been given 5 minutes opening remarks, I only really need a couple. Apparently this is the minimum amount of time they can put in the timetable is 5 minutes. I just want to say a couple of words about the UK CI meeting, because I appreciate that a lot of you think, oh, well, what is the UK CI meeting? I don't understand what's going on, which is perfectly understandable. So back in 2003, the UK CI meeting was set up by myself and Jeff Ridley. Jeff, do you want to stand up? Yeah. Fresh from the catwalks of London Fashion Week, there's Jeff over there. So the reason we set up this meeting, which only really meets annually, but we have informal communication throughout the year, is to try to bring together the disparate CIs that happens in the UK, CS modelling and CS observational work. So we tend to have small pockets of people doing work, and the idea was to try to bring this together. So this has been happening now for 14 years. This is the 14th year, and so this year we decided to bring it into part of this workshop. Okay, so that's why it's happening on Friday. The first 4 days with the multi-scale modelling, and the Friday is the UK CIs meeting. So the UK CIs meeting, although Jeff and I are both on the sort of the modelling side, okay, it's always been about observation and modelling, whether those observations are field work or satellite observations. And I'm pleased to see that later on we do have some more observational talks, which are great because they're essential to drive the spin forward. What else to say? Oh, yeah, you might also note that our first speaker is not obviously part of the UKCS group. Despite quite harsh Brexit regulations about how we now organise our meetings, you will notice a little bit of leakage between the Brits into the first 4 days and some non-Brits into the last meeting. I hope you find that acceptable. We wanted to make the best use of people's time when they were here. So probably only one other thing to mention is that in keeping with the UK style of meeting, okay, we won't have the European lunch hour, okay, so it'll be 1 hour. So, and the other days you've noticed you had an hour and a half hour discussion period after that, stroke digestion. Okay, we have so many talks that we just had to squeeze them in. Okay, and so there's only 1 hour for lunch today. So I think that's all I have to say. So with that, I'd like to hand over to Bruno. We're very pleased to hear him talk about constraining CI's mechanical strength parameters to reproduce deformation fields.
Okay. Well, thanks a lot, Danny. Well, thanks a lot, and sorry for invading the UK meeting. I couldn't come any earlier, so it was very nice of Danny to actually fit me in on a Friday morning slot like this. Okay, so this is work that Amelie Bouchat has done for a PhD with myself, and so basically what I want to talk to you about today is there was a study recently published by Girard et al. That was basically saying that viscous-plastic CIs model are not able to reproduce a large shear strain rate and divergence deformation as observed in the Arctic by satellite data. And the evidence here, we're doing PDFs here, and what you're seeing is the observation in green, okay? And what you see here in blue is the PDF of deformation, shear rate, okay, and divergence, and this is the PDF. And basically there's a lack of large deformation in the VP model, something that is not present in the elasto-brittle model. And so this was argued that this should be an argument for moving away from viscous-plastic CIs model. So if there's only one message that you're taking out from this thing is that VP model can reproduce large PDF, and I'll be showing you why. And maybe another way to phrase this question is that maybe we can use now the deformation field as a way to validate or constrain CIs model. So basically in the past what we've done is we've looked at buoy data and we've adjusted drag coefficient, CI's compressive strength, and we basically used those data to actually get the best match between observation and data. But quickly we found out that this is not enough. As soon as you are shear resistance, compressive resistance, any rheology you're going to use, you'll be able to match buoy observation. So you cannot discriminate one rheology from another just from drift data. Although it's very useful, you want to have the right drift because in part the thickness distribution is a function of the drift. Okay, and also the sea ice export, which is the liquid freshwater export from the Arctic, is a function of the drift speed. So this is a good metric. You want to satisfy that, but it's not enough if you want to go and dig deeper and discriminate between one or the other rheology. Recently, what we've had is like RGPS, which is RADARSAT images, very high resolution, and we're able to calculate shear, strain rate, and divergence at very high resolution. So this we felt was, this is now an opportunity to actually like perhaps discriminate between different rheologies. And then this is a bit what I'm going to be talking about here today, is can we use shear, strain rate, and divergence from RGPS, okay, to actually constrain CIS model, and in this case, viscous-plastic CIS model. And what we see is that there are ways to modify a yield curve in the viscous-plastic CIS context to actually match the observation. Whether you agree with the physics of the VP model or not, that's a different question. But the question that I want to address here is that this, like the idea that VP model behaves as a viscous fluid and that it cannot reproduce large deformation as observed in the observation. This is the idea that I want to dismantle in this talk. Okay. So RGPS, this is the information that we're using to actually constrain CIS model. So you take images, okay, at different times, and then you can actually track feature on the surface, and you can actually calculate like a velocity, and from the velocity on the gridded field, you can actually calculate divergence. This is like an example of divergence, maybe convergence here, okay, shear. And basically what Ron Kwok has done from those images is to derive like a good 10 years of data for winter, where you have the divergence and shear strain rate at a 10-kilometer resolution, also at a 3-day interval. So we're somewhat limited in the temporal resolution. It's a 3-day average, but the resolution is actually pretty good. It's 10 kilometers. Okay. So when we talk about shear strain rate and divergence, this is what we're talking about, like the divergence, okay, defined here, the udx plus dvdy, and this is the maximum shear strain rate. These are basically the strain invariants, okay, for the CIS constitutive equation. So this is what we're going to be, all along you're going to be seeing epsilon dot 1, epsilon dot 2. These are the shear strain rates and the divergence, the first and the second invariant of the stress tensor matrix. Okay, so basically we derive this from the satellite data. Okay, so now if we're looking here at the observation, so what you see here is the shear, one example, like from the RADARSAT, and divergence. So you've seen those images before, I'm sure, but just if you have not, so you see that like shear and divergence are located in this very specific location in the Arctic along sea ice leads. Okay, so you have like active sea ice lead, they're shown here in red, and where you have like more like white or yellowish color, this is where like the lead activity like is smaller. So this is basically like the kind of image that we're getting from RADARSAT images. And where you have large shear, often you have also divergence or convergence. Basically the sea ice sets in motion by you load the ice, you reach the critical load for the ice to actually fail. It fails, then it will shear, and it will shear, and along those shear line will be some divergence or some convergence. So this is basically the mode by which ice is moving in the Arctic Ocean. Okay, so we call these, I'm going to be referring to those as LKF, or linear kinematic features. So this is the observation. You can look at them as well. Like before, here you're seeing like a spatial distribution of LKF. In here, what you're seeing is a PDF, because in the talk today we're going to be looking at PDF and from model and also from observation. So these are the observations that we're comparing against here. Okay, so you can see here that for large deformation, it's a log plot, so it's a power law. Okay, it's a linear like a slope here. The same thing in divergence and in convergence. Okay, and here we're plotting 2, 3, 4 years, like well, all 10 years actually of data, and you can see the variability from year to year is not that large. In the talk here, we'll be taking like a specific year, which is close to the mean, to compare against model divergence, convergence, and shear strain rate. So these are the observations. You're going to see that over and over in the following. So this is the observation versus the model. Okay, so observation on the top, that's the image you just saw before, and this is for the viscous-plastic CIS model. And indeed, you would look at this and you would say, yes, you are missing like high deformation. You don't see any of these red lines. We use like the same color bar here. Same thing with the divergence. Okay, so indeed, like you are missing some of those high shear strain rate and divergence like field with a viscous plastic model with at 10 kilometer and also with control parameters. Okay, if you look at the PDF of the control run, okay, in the VP here in blue, and again, like you got the RGPS here in black. So you see here that you're missing the large deformation, and you have somewhat less of those intermediate deformation as well. Okay, and the same thing is occurring here. Okay, you're missing the large deformation, and also you're missing the large deformation. So indeed, this seems to corroborate like what was published before, and this is definitely an issue. Although like the line here is not nowhere near as like drastic as what was shown in Girard et al. And this may be something that we need to look into more, but nevertheless, there are some large deformation missing in all three of these features. Okay, so basically, so what are we going to do here? We're looking at a way to constrain a rheological model using RGPS data. And what gives you like those LKF, like inside a CI model, it's all defined by your rheology or the stress term here, sigma. And what we have here in the viscous plastic rheology is it's a plastic model for most strain rate. If the strain rate is extremely small, then you're going to have a viscous behavior. You'll see later that this, for all practical purposes, we're running an ideal plastic model. This is something that maybe I want to stress as well, because in the previous literature, people have been describing as a highly viscous and behaving a lot like a viscous fluid. The time scale associated with those kind of viscous deformation is 10 to the minus 4 per day in terms of strain rate, which is 30 years. Okay, and basically when you're looking at LKF formation, we're talking about hours to days. So on those time scale, the viscous term is really not there. Okay, so if ever like there is a discrepancy between what you observe, okay, in the model and the observation, I don't think it's really the viscous behavior that you're like you want to blame, because really there's a separation of scale. We're not talking, the viscous term are not operating on those kind of scale. Okay, so this is one point that I wanted to make as well, based on the previous literature. Okay, so what are we doing here? We're sorry, there was a conversion error here, like with the sigma, but like try to ignore this. So basically, what we have the yield strength. Okay. This is the elliptical yield curve, and then what we've done first is we've rewritten like this elliptical yield curve in terms of P, S, which is like the maximum shear strength, and also T, which is the tensile strength. Typically, like the yield curve, the elliptical yield curve is written in terms of P and the ellipse aspect ratio. This is a trivial like change. It's just a matter of like rewriting the equation, but it's kind of nice because you can modify S, okay, the maximum shear strength, and P independently. Because when you change P and you keep E constant, you're basically changing P and S. So this is just a way, it's cosmetic, but it's a way to rewrite the equation in such a way that basically you can modify both independently. So this is what we're going to be doing here. We're going to be changing P star, keeping S and T constant. We're going to reduce it, we're going to increase it, and we're going to change S, keeping P and T constant, increase, decrease, and we're going to modify T accordingly, and then higher, lower, while keeping S and P constant. Okay. So these are the control parameters that many people use: 27.5 kilonewton per meter square. S, the equivalent S for in an ellipse aspect ratio of 2 is 6.9. Okay, and T is 0. These are your control value parameter. And this is just a way of rewriting the elliptical yield curve of Hibbeler using P and T instead of E, the ellipse aspect ratio. So this is a small detail that we've introduced here. Okay. So basically, as I was saying before, now we're no longer like using drift and buoy data like to actually constrain the model, but rather we're using the strain rate to constrain the mechanical strength parameter of the model. Okay, so basically we're taking a domain, and which domain are we taking? This is the RGPS, and in the red here, or within the white contour here, what you're seeing is the place where you have 80% of the time data from RGPS, and this is what we're going to be limiting ourselves to in order to compare the model to the observation. So we will be ignoring like coastal areas simply because the data is not always there. So now what we have is we always have data in the model, and we have data in the RGPS 80% of the time. Okay, and the very first run, the control run, okay, with a standard P, S, and T. This is what we're going to be doing, okay, the compressive strength experiment. We're going to increase P star, we're going to decrease P star while keeping S constant. We're going to increase S or decrease S, okay, while keeping T and P constant. Again, the blue curve is the control run parameter. And we're going to be keeping P star and S star constant, and we're going to modify T here. And again, the control run parameter is the blue line. Okay, so blue is the control run parameter. So what are the control run results? So this is what I've been showing you before. This is the lack of large deformation in the control run simulation of the viscous-plastic sea ice model. Again, lack of large deformation in the divergence field. Okay. So compressive strength experiment. So you increase and you decrease P star. What do you see? If you increase P star, you're in pink. You basically haven't changed very much. Okay, pink, pink. So increasing P star doesn't change your simulation very much. When you decrease P star, now you're very much in line with the RGPS deformation. You have much larger convergence. You have much larger here divergence. Okay, and you're in line here with the shear. So why is this? Well, if you shear, you're going to have a long shear line convergence or divergence. If you want to diverge, there's got to be some of the places where it will have to actually converge. So basically, if you reduce the compressive strength of sea ice, you're easing shear deformation, because ice, when it shears, needs to diverge at time, and there needs to be space to do this. And the way to do this in this kind of rheological model is that if you weaken the ice in compression a little bit, you're easing shear, because all of a sudden you shear, you diverge or converge, and you make that process easier. Okay. So the reason why we're getting a much better a match is because by lowering the compressive strength, you're basically easing shear strain. Okay, so it looks like if you're reducing your P star or your compressive strength in your sea ice model, you're going to be in line with the RGPS deformation. This is something also that Miller here, and I think with Danny was a co-author on this. But he was arguing for a lower aspect ratio, which basically is equivalent to this, reducing P star. And he was seeing better match between the simulated sea ice thickness and the observed sea ice thickness. And in particular, they were looking there at the mismatch between the Beaufort Sea and the North Pole region, where in the control run simulation, they had a bias. By changing the ellipse aspect ratio, they reduce this bias. So this is kind of in line with that. Okay, this is now looking at it, but more spatially. This is my control, the observation, the RGPS, always the same. This is the control, which doesn't show much of those large deformation. And this is when you reduce P star, you see higher deformation in red here. But you'll tell me, Bruno, yes, you have more, but you're really missing in terms of the lead density. You don't have enough, and this is correct. And I will return to that at the end of the talk.
Can you clarify how do you calculate the model shear and divergence, given that the RGPS is a 3-day estimate?
So what we do is that we output the data every 10, 15, 20 minutes. We have the U's and the V's. We calculate the divergence and the shear, and then we average them over 3 days, and then we compare them with the RGPS. So we do the exact same procedure as what RGPS is doing.
Well, it's not exactly the same.
Yeah. Well, RGPS is, pardon me?
RGPS is a composite.
Yes, and it's also originally a Lagrangian data,
Yeah.
and then basically they gridded it. So we are comparing against the gridded Lagrangian data of RGPS, and because we have a gridded model. So this is something I did not mention. So one thing I want to mention is that a 10-kilometer RGPS data, in order to resolve that with a gridded model, you need about 4 or 5 grid cells to actually resolve a gradient. So basically, if you want to get to those kind of lead density, you will need higher resolution than 10 kilometer. And I will show at the end a slide from Niels Hutter, and then Martin Lush is involved in this, and many Mendes as well, using a 2-kilometer VP rheology. And you'll see later at the end of the talk that the question of the lead density is resolved by increasing the resolution, which is in line with the fact that for a 10-kilometer observational data set, you need a higher resolution gridded model. Okay, but this is why you get the large deformation, And you need to be careful when you see a very good match like this. Okay, it's one thing, but you see that when you look at the lead density, you're totally off, you're missing. So looking at the PDF alone is not enough. Okay, you also need to look at the lead density. When you look at the shear strength experiment, we're looking at the control run, higher, lower. Okay, so when you look here in green, we've lowered the shear strength of the ice in green. And in pink, we've increased the shear strength of the ice. And again, in pink, we get a perfect match with the RGPS deformation in shear. And again, a very much better match here for the divergence. So another way of arriving at the very same result is to increase shear in the yield curve. That sounds a little counterintuitive. You're missing high shear deformation and you're going to increase your shear, you're going to make it even more difficult. Well, it just means that to shear, you're going to have to increase the load much more before you actually shear. But when you do shear, you're going to shear very vigorously. Okay, so if you want to increase your high shear deformation, you actually need to increase your shear strength rather to decrease your shear strength. Okay, so now we have basically two that are almost undifferentiable. Like if you look at this in the previous slide, you'll say, well, okay, now you're in a situation where decreasing P star or increasing S star seems to be giving you the very same result. So all we'll do is discriminate between those two options, and I'm going to show that 2 slides down the line.
Bruno, you just said that for the P star experiment, it was because you eased the shear that it worked well.
I eased ridging.
Oh, I see.
Because if you shear, you're going to need to dilate. You're going to need to have some divergence. If you want to have some divergence somewhere else, it will need to ridge, or and so you want to ease that. Yeah. Yeah. So this is the shear strength experiment again. Like this is the observation, control run, and then here you see line of higher deformation. But again, you see the lead density is not as high as in the observation, and this we will argue later that it's a question of resolution. So when we look at the tensile strength, like a little bit more and a lot more, when we look at this, all 3 curves lie basically one on top of each other. So increasing the tensile strength into your yield curve in terms of your PDF doesn't do very much. It does do something, although like you don't see it on the PDF, but you can see here there will be the appearance of like a single line, extremely active, but very, very seldom like appearing in the simulation. For example, here a very large like shear line north of Banks Island. This is a location where you almost always have a shear line coming off. The shape is not exactly the same. Like in the observation, it's like more like a concave the other way. But nevertheless, like it makes you wonder. Like we know there is shear in sea ice, and is this related to what's happening in the real world? We haven't looked into that very much, but it may be something that we want to look at like in the future. But changing tensile strength doesn't do anything for you in terms of your PDF. It will make some lead appear in some location at some times. Okay. So then the question we ask is, okay, now what do? We reduce P star or we increase S star? Okay, so this is a summary of the 4 figures I showed before, where you had a good match with the green here and you had a good match with the pink here. So what we do is we look at thickness and then we look at drift. So this is the control run, this is the increase S star, this is the reduced P star. When we increase S star, like the velocities here decrease dramatically. When you reduce P star, the velocity remain in line. So based on the drift, reducing P star seems to be a better option, and we can discriminate against increasing S star. Okay. When you look at the thickness field, it's not as obvious. I mean, like both are a little bit less off, but there are also like uncertainties in terms of like the observation. And there's so many other things, like there's a thermodynamic in our model, which is we have a slab ocean and we have a very simple thermodynamic. So basically we have not deteriorated our thickness to the point where we think this is an unrealistic solution.
Is this some kind of mean average picture, or this is snapshot?
This is a mean, I would think. Yes, Amelie. Yes, I'm getting the yes from Amelie in the back. Very, very discreet. Thanks. Okay. Good, good, good. We talked yesterday at the bar. Okay. Okay. So another evidence for this, we can also look at like Veronique Dringer Masters actually look at error in simulated sea ice drift as compared with buoy data. Okay, and she looked at like the ellipse aspect ratio here on the x-axis and the compressive strength on the y-axis, and these are error curves. And you can see that there's a region of very low error here in the middle. So basically, when we look at the control run, we're sitting here, ellipse aspect ratio of 2 and a p star around 27. So we're in that valley there where we minimize the error. When we increase S star, okay, when we increase S star, we're keeping p star constant. So E is also decreasing, and we're getting away from this valley. When we reduce p star, okay, we also reduce E at the same time, basically, by doing that, and we remained along that same valley. So basically, from this result, we argue that, okay, well, this is the reason why the drift is also like again like inline. So basically, like it looks like there's an optimal in both cases. There's an optimal like ellipse aspect ratio. It's suggesting that in the context of a viscous plastic model with an elliptical yield curve, the CI should have weaker compressive strength and larger shear strength. This is what, in this context, this is what it's suggesting. Okay. So this I said before, it's in line with result of Miller et al. Okay. So conclusion, and I have a few more slides before, so don't worry, like I'm going to take 10 more times of your time, 10 more minutes of your time, but I will not take the full time so we can actually discuss all together at the end. VP model can reproduce the observed PDF and spatial scaling if the aspect ratio of the ellipse is reduced. Spatial scaling I have not discussed, but this is done actually on a poster here in the back by Hutter and then Martin Losch. It was done by Gunnar Spreen as well. In our recent paper with Amelie, we also look at spatial scaling. So basically, the spatial scaling is less of a compelling story. Everyone has a bit of difficulty, like reproducing, like the slope, but like the VP model that we showed you also respect those like a spatial scaling. And I believe yes, and yeah, Niels, I said that like in the poster there, he's looking at this too, with a much higher resolution model. Okay, so on the question of lead density. What Hutter, okay, I have Hutter and Losch here, but many-manless as well was also involved in this, like in producing a high-resolution MIT GCM run. I believe it was 1 or 2 kilometer. 2 kilometer, Martin? 1 kilometer. Good. So it's a 1 kilometer resolution. It's an animation. I'm sure, like, if you email like Niels or Martin, they will give you like the link. Basically, this shows you the lead density. And basically, when you look at the lead density, and if you were to animate this field, you would see like a very realistic like a field of deformation and of density of lead, basically, when you compare with the RGPS data. So this is the data, Martin, this is the data that you've used on your poster for the scaling. So basically, you'll see the scaling analysis for the deformation based exactly on this data, like outside here. Okay. So basically, so on the question, so what we've done 10 kilometer run, and so we matched the PDF and we matched the scaling up to 10 kilometer, but we were off in terms of the lead density, but we believe that resolution is the solution, is the cure for the lead density problem. Okay, so some thoughts. So this is like this is just me thinking out loud now. Like some thought on why the lead pattern is in line with observation. Okay, in a viscous plastic CIS model. Okay, and here I'm talking always like in my mind in comparison with like the in line with the elasto-brittle like approach. So when you look at the constitutive relation of a viscous plastic model versus that of an elasto-brittle model, so this is your constitutive relation. The first thing you notice is that this is epsilon dot and this is epsilon. Okay, one is looking at strain, the other one is looking at strain rate. Okay. So there's a time scale involved difference between the two. If I make a mind experiment where I keep H and A constant, I'm starting at rest. So basically, there will not, in the divergence of the sigma term, there will not be, this term will not be important because it's like P will be constant. So now what if I look at the eta, which is like your shear viscosity, and then this is the bulk viscosity minus the shear viscosity in a viscous plastic rheology. In the elasto-brittle, what you have is here like the shear modulus, okay, and lambda, like those are the Lamy coefficient in the linear elastic solid. So what if I calculate those parameters here, okay, in both rheology, what I'm getting here is those number for the viscous plastic rheology, and I'm getting this for the elasto-brittle, and the time scale associated with like the time scale difference, because one is per second square, one is per second, is of the order of 6 hours. So if I look at my shear and bulk viscosity and divide them by 6 to 12 hours, which is a right order of magnitude for the formation of a shear line, basically I'm pretty much getting the same, I'm basically solving the same equation. So if I start from rest, then one would think that would build up stresses, and in case, I've shown result with an elliptical yield curve, but we can also use a more Coulomb, just like in the elasto-brittle model in the viscous-plastic context. And there are reasons to believe, when I look at this, that you would get the same stress field, you would reach the yield curve at the same time, basically. Okay, but you'll say, well, but Bruno, you have a viscous term here. Okay, I have a viscous term, but the characteristic time scale for the viscous term is 30 years. Okay, it's 10 to the minus 4 per day, as per Hilbert 79. That's a 30-year time scale. The characteristic time for an LKF is hours or day. So basically, the viscous term is not really entering here. Like, so we're basically solving, I believe, very similar equation. Okay, okay. So now on the flow rule, we're talking about elliptical differential equation. An elliptical differential equation is one where the solution is set by the value on its boundary. Okay, so what sets the stresses on the boundary? Well, in case of the viscous-plastic rheology, it's the normal flow rule. You fail, you shear, and then you will dilate more or less. The flow rule will set the stresses on the boundary, and therefore the stress state inside the ice flows. Okay. So we know the elliptical yield curve and the normal flow rule. We know that this was done like for some kind of ductile material like metal. Everyone knows this is not applicable to sea ice. But one could use a VP rheology with a more Coulomb rheology, a double sliding model, which is much more realistic. Okay, but it's still parameterized. Okay, the flow rule is that you fail, how are you going to deform? That's going to set your stresses at the edge, and therefore it's going to set your stresses within your flow. In the case of the elasto-brittle model, what's going to set that is your damage function. You fail and you damage the ice. Do you damage the ice a lot, or do you damage the ice less? That's going to set your stresses at the edge, and therefore it's going to set your stresses inside the field. Okay, so a question that I would ask at the end of my talk, normally like people ask the speaker, but me, how sensitive is the simulation of an EB model to the choice of damage function? Okay. Is it very sensitive? This is something that I would like to know. Like, if, I mean, we're starting to use this model, so we're going to find out. But at the moment, I don't quite know. Okay, so for the VP model, the normal flow rule or double sliding rule for more Coulomb, for the EB, okay, is largely set by the damage function. So both flow rules are highly parameterized. So I would say somewhere where we would need to look at a bit more in details is like what is the effect of the flow rule onto your deformation, onto your PDFs, and whatnot. Okay. So the next step, I would argue, is okay. So we looked at drift, and we can get a good match, but we can't discriminate between rheologies. Now we go to strain rate, and then I'm showing to you that you can have like an elliptical yield curve with a normal flow rule, and you can still match the RGPS deformation. So you still have not found a data set that enables you to discriminate between one and the other rheology. So what do we need now? So next, I think we should look at the lead density, intersection angle of leads, okay, and lead orientation. And this is something I think that came up like as a resolution out of the famous meeting a year ago. And so these are recommendations by this group at the famous meeting, like in Woods Hole. And I think this is a good idea. So maybe then we will be able to discriminate between, because maybe like the lead density, maybe the density is not the correct one in the right places, because this will have an effect on heat flux to the atmosphere, salt rejection into the ocean, also like ventilation of the thermocline. When you have shear along the leads, what you have is Ekman pumping. When you have Ekman pumping, you're pumping up stuff from beneath the mix layer. You're bringing heat from the previous summer that was not ventilated. You can bring nutrients as well up to the surface. So basically, maybe like now this would be a way forward in order to discriminate and maybe like get a better handle at what you need in terms of a rheological model. Spatial variation of lead density may be the most important for climate application. Yeah, like you want to know how much heat flux goes to your atmosphere, how much salt is rejected to the ocean when you're doing climate modeling. And that's it.
Thank you much, Bruno. Can we have questions now, please? And can you please make sure you speak very loudly, because the room is quite full now, and people at the back can't hear you if you're speaking at the front of the speaker. So make it nice and loud. So was it Court?
Yeah.
Yeah.
So you mentioned you have a slab model, and can you say something else about where the wind field came from, and how the uncertainty and the currents in the wind play into the analysis?
So we have we're running our model with NSAT winds. So they're extracted I think it's daily data, and then when we run our model maybe at 20 minutes time scale or 10 minutes, then what we can do a linear interpolation between the two closest dates. Okay, and basically we've looked at modifying the winds, but at the beginning, and you can. I mean, basically, the wind have most of its power. There is shear in the wind. Okay. So basically, if you have shear in the wind, one might expect if you had an ocean underneath that, you'd have shear in the ocean. But where you have most of the shear in the wind, the ice is able to resist. So basically, this is not what drives the deformation PDF statistics. Those kind of shear are able to be the compressive strength and shear strength of sea ice is able to take it. And basically, you have much higher deformation. Why? It's because the wind integrates over long distances where the load picks up, and at one point the ice can no longer take it, it fails and then it shears. So, but basically we've modified the wind, it will modify those PDF as well. If you were to increase the wind or decrease the wind, it will have an impact. Amelie, you remember you had done some simulation at the beginning where you modified your winds, and it had an impact on the PDF, I'm correct?
Yeah, well, like you said, where we have the highest shear in the winds, we couldn't reproduce the high shear in the sea ice. We could only get that if we made our ice completely viscous.
Yeah.
But that's not what we're doing. So.
Yeah, much weaker ice would follow the PDF of the wind, basically.
Just to quickly clarify, the currents in the slab model.
Oh, so this is good. So we run our CS model for 30 years, and we look at climatological ocean current, and we fix the ocean currents spatially. So there's no dynamical ocean. It's a specified ocean that does not vary with time. It's a very simple setup, but we've put our energy into the rheology there. We have the JFNK numerical solver, and basically we're looking at we're using this model to actually study rheological questions.
Okay, so our next question is Veronica.
Well, my first comment, I think we can talk about this later, but I think there's a comprehension problem about the fact that in the EB we don't prescribe at all the relative amount of stresses on the damage envelope. So maybe we can talk about this later. This concept that's maybe hard to get, but that wasn't really clear from your talk. My main question is: have you done any type of analysis in time?
In time, you mean
scaling analysis?
Scaling, temporal scaling?
Yeah, Fourier transform, seeing how are your signal varying in time?
No, we haven't done that yet. No. But in terms of the stresses, I'm not talking about specifying actively the stresses on the edge. What I'm talking about is the nature of the differential equation. Elliptical equations are defined by stresses on boundaries.
Oh, you're talking about flow rules and
the flow rule, yes.
Stresses. There's no flow rule in an EB model.
Well, your damage function is a kind of flow rule, because if you're weakening your ice somewhere, it will ease the flow. So it will affect your. If you were to damage your ice a lot or damage your ice not at all,
Exactly.
you would have very different flow field.
I think that's a discussion, because
Yeah. Okay.
I'm not sure I know that's a rabbit hole. Okay. There was another question, I think. Jeff Ridley had a question.
So the RGPS data, it misses out the diurnal variations in the ice, and therefore you're going to have, through your snapshots, you're going to generate artificial strain rates. How can you take that into account in your PDF?
Can you repeat your question? I'm not sure I'm
So there's diurnal oscillations in the sea ice, and so the vector of motion is going to be undersampled from three days. So you're going to generate observationally based shear and strain rate.
Yes, that's correct. But this is the best we have, and this is all we can use so far. if we had a higher temporal resolution, we could do like a better analysis, and it would be more useful. But I don't know that we have any ways. We have an error estimate on the velocities, which gives us an error estimate on the deformation, and this is what we use to actually give an error bar on those estimates. But I'm not sure we can do more than that. Or do you have any suggestions?
Okay, so I think Vizor's desperate to ask something. Or say
So
something.
that was related. Jeff's question is following what I asked you to clarify in the beginning, because you calculate the 3 daily vector motions by basically calculating the distance of a feature that is tracked by RGPS, and you divide that distance by 3 days, and that's your velocity.
Yeah.
And actually, you need another pair of 3 days to repeat that to calculate the stresses of deformation. So it's not a 3-day field; it's a 6-day field. Because to cover the whole Arctic, you need 3 days. You need to repeat to track your features to get the velocity from distance and time. So you have now 6-day mosaic composite picture from RGPS. My question initially was how you compare the model, because if you do 6-day average from the model, you're removing a lot of deformations from your model field because you're averaging them out. And in the RGPS, some of them, because of the storm motion, they might be actually the same response, but in a different location over a 3-day period or over a 6-day period. So one way of doing this actually is averaging in the model less, which there's no good solution, or extracting the RGPS tracks from the model, satellite simulator, exactly so along the same track, and do exactly the same with RGPS.
We had, well, we considered both ways, looking at the gridded data set or looking at Lagrangian tracks and doing this. At the end, we opted for the gridded data set, doing the Lagrangian analysis. It would be possible, and it's something that we could do. But this is not something that we have decided to
What
do.
Jeff is saying, that RGPS is missing some of the sub-daily cycle response, and also some of the density of your LKEs in a model is related to averaging them out. It's not only resolution. Resolution is one thing, but there's other components.
I see what you mean.
We need to press on, I'm afraid. So there are a number of extra questions. I'm sure I have some, but we should move on to the next speaker now. So thank you, Bruno. So David Rees-Jones, up front, please.